Here we have a 5 kilogram penguin sitting on a 10 kilogram sled. I like to redraw this and remind myself that, while we might think of forces as some really active thing exerted by an agent on an inanimate object, all of these objects take part in forces, which are relationships between two objects. A force is always a relationship, a two-way street. So we have a 5 kilogram penguin. I'll just impersonally draw it as a box here, and it's sitting on a 10 kilogram sled. That sled is pulled to the right by a 45 Newton force, and we see that the coefficient of friction between the sled and snow, as well as between the sled and the penguin, is 0. So we've got a coefficient of kinetic friction, 0.2 at this interface, coefficient of friction, 0.2 at this interface. Now our next step is to draw free body diagrams for each of these bodies. First, for the penguin, I see that the tension is acting to the left on the penguin. There is going to be a frictional force on the penguin's feet acting to the right. I'll call that F sled on penguin. Maybe it's a pain to have such a long subscript here, but I like to be explicit about what is happening. I have a normal force here. That is the force of the sled acting upward on the penguin. And I have the penguin's weight. That is 50 newtons, 5 kilograms times g equals 10 meters per second squared, so a force of 50 newtons down. Now let's take a look at the sled here, color coding. I've got a second free body diagram. Pulling to the right, obviously, is a force of 45 newtons. I have two friction forces, one due to the penguin and one due to the snow. So the top force is going to be counteracting. It's going to be proportional to a normal force. Which normal force is it? It's the force that the penguin exerts on the sled. Since the weight of the penguin is 50 newtons, I can see that this force here will be a force of friction equal to mu times that normal force. That normal force is 50 newtons, so this is 0.2 times 50 newtons, or 10 newtons. Now this bottom force here is proportional to the normal force that the snow exerts on the sled. Now the snow is supporting not only the 100 Newton weight of the sled, but also the 50 Newton weight of the penguin. So here this force is going to be equal to mu times the normal force of penguin plus sled, which is 150 newtons. So that is going to be 0.2 times 150, that's a fifth of 150, or 30 newtons. Completing this free body diagram, I have downward the force of the penguin on the sled, and here this notation makes explicit force of sled on penguin and force of penguin on sled. Those are equal but opposite Newton's third law forces. We also have the normal force here. We know it's actually much longer than this, but I ran out of space. This is going to be equal to this normal force is the force of the snow acting up on the sled. Now I'll highlight the direction of motion, or lack of motion, the direction we want to analyze these forces. So I see what's happening here. This penguin straining to not let go of the rope. We can assume that the penguin has got a tight enough grip. I don't know how that works without opposable thumbs in your fins, but the penguin has a tight enough grip that the penguin will not accelerate. So the acceleration of this penguin is 0. That makes this an example of a problem called a statics problem. So here we have, what is the net force acting on the penguin? Well, we have F sled pulling to the right. I'll call that F, minus T is equal to ma, which in this case is 0. The m we're talking about is the mass of the penguin, which is 5 kilograms, but 5 times 0 is 0. That F force is F of the sled, and I can see from that simply that F sled, the force that the sled exerts on the penguin, is equal to the tension. Now we want to make note of an important action-reaction force pair here, the force of the sled on the penguin, which is a force parallel to the interface between the penguin's feet and the sled, and the force of friction here. So these two forces are equal but opposite, this friction force and this friction force here. This is the force that I've called F, so I know that it's equal to the tension. Since I already know what this friction force is, that tells me that the tension is 10 newtons. So that has solved part B of this question. We also want to know the acceleration of the sled. Let's set up Newton's second law to figure that out. I see that I have acting to the right, which I will take to be positive, 45 newtons, minus the 10 newton frictional force of the penguin's feet, minus the 30 newton frictional force of the snow, is equal to ma, the mass of what? The mass of the sled in this case. So that's equal to 10a, 10 kilograms. So we have 45 minus 40 is equal to 5 newtons net force equals 10 kilograms times A. A is equal to 5 newtons over 10 kilograms equals 0.5 meters per second squared. So that will be the acceleration of this sled as it's pulled out from under our poor penguin.